Hello, welcome to Unit 5 of AP Physics C Mechanics. This is Unit 5 Rotational Dynamics. This is going to be about making objects spin. We're going to cover the equivalence of distance, velocity, force maths, but for rotation. So we're spinning things. So first off, rotation is the circular movement of an object around an axis or center. That is the circular motion of all the particles within an object. And basically, the thing that we use for this is the same thing for just normal kinematics. So the angular velocity is omega, the angular acceleration is alpha, and the angular displacement is theta. And the relationships between each of them is the same as the relationships that were in the kinematics equations in Unit 2. So it's literally the same thing, but that it just has different names. So you probably should get used to the names. Anyways, because we mentioned how circular motion is the composite motion of all the linear motions of each particles within an object, the linear displacement of a rotating object is radius multiplied by angular displacement. This applies to literally every part of the rotational dynamics thing. So radius multiplied by theta, the angular displacement, is linear displacement. Radius multiplied by omega is linear velocity. Radius multiplied by alpha is linear acceleration. So that is the very beginning of torque and rotational dynamics. And now we have to talk about torque. Torque is force multiplied by distance. It is exerted from the axis of rotation. This is not necessarily the center of mass. Sometimes it is, but other times it's not. We have to know the axis of rotation to know the torque. So torque is the equivalent of force in linear motion, and as you probably would have noticed, the distance it exerted from the axis of rotation is dependent on the angle in which the force is being pushed into this object. So the force component perpendicular to the axis of rotation is all that matters when you're trying to get the torque. And the reason why I have this little diagram is for that reason. So if we're trying to find the torque for A, we have to know sine 90 degrees multiplied by R. The reason why we multiply sine 90 degrees is because we need to find the force vector that is perpendicular to this axis of rotation vector. Basically, we need to find the force that presses straight down into the thing that we're trying to rotate. So for A, we know that it's already perpendicular, so it's sine 90, so it's going to be 1, so it's just going to be force multiplied by radius. And if we're trying to do B, it's going to be sine theta multiplied by 2r multiplied by force. The reason why is because the axis of rotation in here is twice as far in B than A, because the axis of rotation is in here. So that's the reason why, and we don't know theta yet, so we just put theta in sine. Same goes for C. We know that C also has the angle of theta, just in the opposite direction, so that's why the minus sign is in here. And it's also 2r because it's also the same distance from the axis of rotation as B is. And then D, it's 3r from the axis of rotation, but it's also 90 degrees, so it's perpendicular, so you don't have to use theta. So it's just sine 90, which is 1, so F multiplied by 3r is going to be the torque. And then the next concept that we're going to have to talk about is rotational inertia. So in linear motion, mass is the measure of object resistance to acceleration. So one thing that we really confuse between like rotational inertia and just linear inertia is that linear inertia is just mass. We confuse mass and inertia so much, but it's the same thing. So given that rotational inertia is the equivalent of mass in linear motion, but that we also have to know that this is rotation, so it is kind of different. So how we get rotational inertia? It's mass multiplied by distance from the axis of rotation squared. The reason why we have to measure the distance from the axis of rotation is also the same reason why we have to multiply r when we're trying to get the velocity, acceleration, and displacement, when we're trying to get the linear velocity and all that. We have to understand that the rotation is adding to the linear linear movement. So that's why we add r. So dm multiplied by dr is the inertia of one particle. But when we're thinking about a rotating object, it's probably not just a singular point, right? Because of that, we have to do an integral. So from 0 to r squared dm equals I of the entire object, the r squared being the dr multiplied by dr, 0 to r meaning from the center to the periphery, and that all added together is the rotational inertia of a singular solid object. Another interesting thing that we can look at is an object in which the axis of rotation is different from the center of mass. So this is the center of mass inertia. When the axis of rotation is the same as the center of mass, and that is what adds to the inertia of when it is the center of mass. The method in which you derive this equation is listed here. So when we think about a new radius caused by a change in the axis of rotation from the center of mass, we would probably think of it like that. A new r, which has r plus d, d being the distance from the axis of rotation and center of mass, and we put all that into the equation that we had in here, the integral one, and we integrate it. So it's pretty complicated, but you will realize that this part will become this, and then this two parts will become that. So if you want to know the proof, you probably should look at the study guide. The next thing that we're going to have to talk about is rotational equilibrium. So the thing that makes it similar to linear motion is that in rotational equilibrium, there is no torque. Same as how in a linear equilibrium, there will be no acceleration. There will be no force. Sorry. I don't know why I wrote this. This is wrong. I have to write will not change. Rotational equilibrium is broken when the inertia changes or the torque changes, because we basically define rotational equilibrium based on this equation. So when the rotational acceleration changes, the rotational equilibrium changes. And in order for us to change that, we need to change either the torque or the rotational inertia. Same how it's like similar to the equation that defines linear equilibrium. Rotational motion and linear motion is literally the same thing. It's just that everything is multiplied by r. And usually r doesn't change. Yeah, and that's the relationships that's written there. So similar to linear motion, it's rotational acceleration multiplied by t equals the rotational velocity. Rotational motion multiplied by t being the rotational displacement, the same thing. Another thing being that the slope being the acceleration, the rotational acceleration, and the graph of rotational displacement and time having the slope of velocity. And this is the equations that we have for this unit. So the equations until here, we literally have the same thing from unit 2 kinematics. These two are the important ones. Oh wow, I can't spell important. They're important because it helps us transition between rotational and linear. These are new concepts. Remember how to calculate inertia. It's very important. And we need to know that they are all composites of the different particles within a system. And we need to know that sometimes the rotational inertia changes when the axis of rotation is different from the center of mass. And that shows the rotational equilibrium. So that's unit 5 of AP Physics C Mechanics. I hope you liked it.